Hi there, Organic Chemistry 1, Chemistry 3101. This is Chapter 7, which deals with alkyl halides, nucleophilic substitution, and elimination reactions. A big chapter, so let's get started with Section 7.1, which is an introduction to what an alkyl halide is. And what we're going to see is that alkyl halides are going to undergo substitution and elimination reactions. So the types of substitution reactions we're going to look at are called an SN1 and an SN2. We'll actually look at SN2 first, but anyhow, those are the types of substitution reactions we look at. And the elimination reactions that we're going to look at are called E1 reactions and E2. Again, we actually look at the E2 first, but the idea still stands there that we look at E1 and E2 reactions. So it says the alkyl halides undergo substitution and elimination. Well, keep in mind that in order for something to be classified as an alkyl halide, you have to have your halogen, X, right? So your halogen, that has to be attached to an sp3 hybridized carbon. So this would be considered an alkyl halide when your carbon attached to your halogen is sp3 hybridized. These are not alkyl halides, right? If you look at an aryl halide or a vinyl halide, these are not alkyl halides, okay? So not, okay? I know it says aryl and vinyl, but not alkyl, okay? Not alkyl halides. And so these will not be involved in substitution and elimination reactions. These are actually covered, I think, in chapter 28 of our textbook. So if you're dying to, look ahead, you could go into that chapter 28, and read about that if you wanted. But again, what we're going to be concerned with in this chapter are halogens attached to just your everyday sp3 hybridized carbon, which again gives us an alkyl halide. Well, let's talk a little more about these substitution and elimination reactions. So an alkyl halide can undergo a substitution reaction when it's reacted with a nucleophile. Remember, a nucleophile is a nucleus lover. It loves positive charge, right? We have a dipole here. If we have a halogen, let's imagine this is maybe a bromide or a chloride, right? That's going to be a leaving group. Well, the nucleophile, right? If this carbon is delta plus, right? Well, the nucleophile can come in and it can attack that carbon, and then we'll lose the halogen as a halide, our leaving group, right? Because it's going to be the conjugate base of a strong acid. And there we have a substitution reaction. In an elimination reaction, we take our alkyl halide and we react it with a base. So again, substitution is a reaction with a nucleophile, whereas elimination is a reaction with a base. And how does that work? Well, let me show you. If you take a look at this methyl group here, I'm just going to illustrate one of the protons. And what happens is that you eliminate a hydrogen from the molecule as you eliminate the halogen from the molecule. So sometimes we call this dehydrohalogenation, which I'll talk a little bit more about later on. But the base is going to remove the proton, and then we're going to have the loss of leaving group simultaneously. So it's kind of a 3 steps in one here, right? We're doing a proton transfer, loss of leaving group, and we're forming this pi bond, which is manifested over here in this molecule. This is called isobutylene. Now, you might be wondering, and this would be a great question. I've been asked it before, students would say, well, what about something like hydroxide? That could be a nucleophile or a base, depending on the situation. So how do I know when my substrate or when my alkyl halide is going to undergo a substitution or an elimination reaction? Well, actually, that's going to be a major consideration in this chapter. It's what we're going to talk about a lot. So again, when that reagent, like a hydroxide, okay, can function as a nucleophile or a base, you're going to see that you're going to get a competition between these reaction pathways, right? Sodium hydroxide is an ionic compound. It consists of a sodium cation and hydroxide. So hydroxide is a strong base. It's also a good nucleophile. We get an oxygen with a negative charge. Heck yes, that's a good nucleophile. So in this case, when we take this molecule here, this is called 2-chloropropane, or you could call it isopropyl chloride. Either way, you see that we get some elimination product, and then we get some substitution product. So to produce the elimination product, the hydroxide was behaving as a base, and to make the substitution product, the hydroxide was behaving as a nucleophile. So you heard the word substrate slip out of my lips a couple of times here, And whenever I talk about a substrate, which I'm going to say all the time from now on, I'm referring to the alkyl halide. So this guy here, this is the substrate. So, and if you're like, well, isn't it kind of like the starting material? Well, you could also call this a starting material too. So it's the starting alkyl halide. We call that the substrate. It just sounds kind of fancy, I guess. Well, what happens is if you were to do this reaction with this specific substrate, what you would find is that the elimination product in this specific case would be the major product, and this would be the minor product. And again, what we're going to be able to do once we finish this chapter is we're going to be able to evaluate or predict which one would be the major and which one would be the minor product. So the reasons why alkyl halides can undergo these reactions, these substitution and elimination reactions, I bet you that you could have told, explained these to me already, but I have them here on a slide just to kind of put it down on paper for you or on a screen. The first one is that the electron or the halogen is electron withdrawing, right? There's no mystery there. I'm not telling you anything that you don't already know. We've looked at dipoles a billion times. In chapter 6, we talked about what makes something electrophilic. And of course, if you have a dipole, that's going to render the carbon partially positive. So it's going to be a good electrophile. It's going to render it susceptible to what? Nucleophilic attack. Well, the other reason is that a halogen, when it becomes a halide, the halogen acts as a good leaving group. And I even told you what a good leaving group was in chapter 6, because in chapter 6 we talked about LLG, and I told you that we would talk about leaving groups more in chapter 7. But I know, because I did it yesterday, I told you that a leaving group was the conjugate base of a strong acid. Well, what are some strong acids? Things like HCl, HBr, those are strong acids, right? And the conjugate base of HCl is chloride. The conjugate base of HBr is bromide, right? This is the kind of thought process we want to have. So, scientists love to put things in tables, so that we can just look at it and get the 30,000-foot view. So this is a table. Table 7.1 comes straight out of your textbook, and it says that good leaving groups are the conjugate bases of strong acids. So you've heard me say that several times. Now you have it in writing. Another way you could say it is that a good leaving group is the conjugate base of a strong acid, or you could say a good leaving group is a weak base, right? Think about it. If it's the conjugate base of a strong acid, it's going to be a weak base. So what are the strong acids that we're going to be concerned with that are going to produce good leaving groups? Well, I'm going to zoom in here a little bit. The acids that we're going to consider their conjugate bases as good leaving groups will be these ones here. These are the ones that are going to come up all the time in this class. So basically, any acid that has a pKa less than 0, okay, its conjugate base is going to be considered a good leaving group. So what do I have? I have hydronium, which has a pKa of -2. What's its conjugate base? Water. So water is a great leaving group. Here we have something that has a pKa of -3. This is called a sulfonic acid, and I know you've seen sulfonic acids before, but I'm just going to mention it again. So this is a sulfonic acid. So this is called a sulfonate ion, a sulfonate ion, okay? This is actually called a a toluene sulfonate ion, but that's neither here nor there. Whenever we see a sulfonate, it's going to be a good leaving group. Then we have HCl, HBr, and HI, and you can see that they increase in acidity, going from Cl to Br to I, right? Going from hydrochloric acid to hydrobromic to hydroiodic acid. And so the iodide, bromide, and chloride, these are all good leaving groups. What are they? They're the conjugate base of strong acids. So these are our strong acids right here. The reason why fluoride is not a good leaving group, you might think, well, all halogens would be a good leaving group. Well, the pKa of hydrofluoric acid is 3. It's greater than 0. And so fluoride is not considered a good leaving group, right? Likewise, you think about something like hydroxide or ethoxide or T-butoxide. Any alkoxide is not going to be a good leaving group, right? And then amide, which is this ion here, it's going to be a horrible leaving group, right? Because it's the conjugate base of a super weak acid. All right, so there you go. So good leaving groups. I mean, what are the leaving groups that you're going to see all the time? I mean, obviously, since we're talking about alkyl halides, you're going to see these 3 most of the time. You're going to see water some of the time. And then as far as sulfonates go, I can't remember exactly, but I think it might be mostly in section 7.12 that we're going to see sulfonates show up when we talk about substitution and elimination reactions with alcohols. So yeah, those are going to come up later, so don't stress about those a whole lot. So again, what's the take-home message from this slide? If I only had, seconds to teach you this slide, I would say, well, these are going to be good leaving groups. You're going to see them all the time in this chapter, okay? Water is also a good leaving group. All right, there we go. Let's talk a little bit more about alkyl halides. So alkyl halides are compounds where a carbon group, the alkyl group, is bonded to a halide, whether it's fluoride, chloride, bromide, or iodide, or one of the halogens. And you remember from the alkanes chapter, chapter 4, the steps that we used to name a molecule. What did we do? We identified the parent chain. We identified the name of the substituents, right? Methyl, ethyl, propyl, isopropyl, butyl, terbutyl, secbutyl, isobutyl. Then we also have chloro, right? Fluoro, bromo, iodo, okay? Those are also substituents. We assign a locant or a number to each substituent, so a 3-chloro, a 2-fluoro, whatever. We assemble the name alphabetically. We ignore prefixes except iso, cyclo, and neo. And the halide group is the key substituent that we are going to name and locate when we only have a halogen. So if you have a chiral center, of course, you have to indicate the stereochemical configuration at the beginning of the name. So if we just take a look at these examples, just to kind of get the ball rolling here, you can see the longest carbon chain here is 3 carbons, so that's a propane. You have the chlorine on carbon 2, so that's where 2-chloropropane comes from. Next, we have the longest carbon chain, which is 1, 2, 3, 4, 5 carbons. We number it so that we give the first substituent the lowest possible number. You can see that both substituents are on carbon number 2. So we have a 2-bromo and a 2-methyl. We put those in alphabetical order, right? Bromo comes before methyl. And then this one here, we have a bromine. We have 1 stereocenter. The bromine is coming out in front. We have a hydrogen in the back. This is highest priority. This is second. This is third. We're going like this. So this is R clockwise. So we have our stereochemical configuration. We have a 5-bromo, and then we have 3 methyl groups. We have 1 at carbon 2, 2 at carbon 3. So 5-bromo, because again, we're going by alphabetical order here. 2, 3, 3 trimethyl heptane. And then of course we put the stereochemical configuration at the beginning. Now remember, the alkyl groups and the halogen groups, those are just going to be listed in alphabetical order. Okay, we don't give any precedent to the halogen. Let me show you an example of where we don't give precedent to the halogen. I know there's not a ton of space on here, but I have a specific example that I wrote down here. So if we have this many carbons, we have an iodine here, and then we have an ethyl here. Okay, well, the longest carbon chain here has what? It's got 1, 2, 3, 4, 5, 6 carbons. Remember, the iodine doesn't take any special precedent. Okay, it's the same. It doesn't take precedent over an alkyl group. So we have a 3-ethyl, right? And then we have a 4-iodo. And you might be thinking, well, why didn't you number the compound going this way? 1, 2, 3. Because when you have a tie like this, you go in alphabetical order. So E comes before I, and so the compound here, this would be 3-ethyl, I'm going to run out of space, 4-iodohexane, okay? And that's just a specific example to show you that the halogens don't take any special precedence, okay? The halogens are always treated as substituents, so we could even write that over here. We'll just write halogens treated as substituents. Okay, they don't take any order, any special order like an alcohol or something like that. Okay, there we go. So how do we put these alkyl halides together? Well, there's a couple of ways that are recognized to name alkyl halides. We can use the IUPAC nomenclature, the systematic names like we have here in this slide, or we can use common names. Okay, so when we do the systematic name, and that's all we've looked at so far, we say chloroethane, right, for this compound. So we have the chloro first. So we name it as a haloalkane. First we list the halogen, then we go with the alkyl or alkene. When we use a common name, and again, common names are called common for a reason, we really only use common names for alkyl halides for small alkyl halides. And as long as you can name the alkyl group, you can name it as an alkyl halide. So since you have an ethyl, this would be ethyl chloride, right? If you take a look at this compound down here, this is a solvent that's used all the time in organic chemistry. Okay, some of you might have even used it in a lab before, maybe in a Gen Chem lab. It's CH2Cl2. Well, I can call that dichloromethane, right? Because you're basically taking a methane and you're substituting it with two chlorines. Or I can call it methylene chloride, right? I'm naming this a CH2 is called a methylene, and then we have chloride, right? So at the end. So again, either way is completely acceptable. But again, the only time we're going to use the common names are for things that are really small. So if the alkyl group is not a methyl, ethyl, propyl, isopropyl, butyl, tert-butyl, sec-butyl, isobutyl, I won't use a common name with you. I mean, there might be some exceptions to that, but it would be something that you would definitely know. Okay, I'm never going to surprise you like, oh, by the way, now you need to know a new alkyl group that I didn't teach you. Okay, that's not going to happen. Okay, that's not the point of the class. Well, with that in mind, let's see if we can name some compounds. This one's kind of cool because determining the stereochemistry here at this one is not, you know, super simple because you notice the methyl group is lowest priority, right? And you have the iodine, which is 1, bromine would be 2, this would be 3, but then the lowest priority group is down here. So you got a couple of options. You got several options here, actually. One option would be to rotate this bond, okay, and put the methyl group in the back. You could totally do that, and then that would look like, oops, that is, it would look like, come on, thinking too fast here. It would look like this. If you had the methyl group in the back, then the iodine would be coming down, and the bromine would be like this, okay? And there's nothing wrong with that. There's nothing wrong with that at all. And then you can see that you go from, you know, 1 to 2 to 3, right, like this. So it's S. So we know the compound is S. And again, there's nothing wrong with rotating that bond. That is totally an acceptable strategy. But let me show you there's another way to do it, okay? And I want to see if you can follow me on this. Just delete all this spinach here just for a second. Okay, so another trick, and the reason I'm bringing this up is because sometimes I'll have students do this, and I want to make sure that you know that it's okay to do it. So if the hydrogen is here, okay, it would be in the back if you were looking at the molecule from the top, right? If your eyeball was on the top looking down this bond, well, then the hydrogen or the methyl group would be in the back. Is everybody, can give me a thumbs up if you just see where I'm going with this? That you have the lowest priority group, it would be facing away from you if you were just looking down that bond. Okay, cool. So then, I mean, you can either, there's two options here, and this is where it gets funny sometimes, because when I teach the class face-to-face, you know, sometimes the students will bring in their tablets, or they're looking at scratch paper, they're making notes, some people print out the slides. And this is really funny, is you'll actually see students pick up the sheet of paper and they'll manipulate the sheet of paper, even though if you just twist a piece of paper, it doesn't change the orientation of the molecule, but it helps you visualize, okay? So another option is just to imagine yourself looking down this bond, and you go from 1 to 2 to 3, and that is going counterclockwise. So that is S, okay? Another option, give me a thumbs up if you understand that. And it's, I know I'm asking for a lot of interaction here, but so, and if you're like, I'm not sure about that, Mr. Dion, well, what my students like Bruna says she's following me. So what Bruna is seeing in her mind's eye is this. She says, okay, if I'm looking down that bond, I have the bromine over here, I have the iodine over here, and then I have the isopropyl group down here. So I'm going from 1 to 2 to 3, like this, which is S, okay? Anyhow, again, it's a strategy that I like to use. I know that some students like to use it, and there's nothing wrong with it. It's a great strategy. So any one of those strategies totally works. I know that was quite a bit of a departure into stereochemistry land, but I think it's important. So now that we've evaluated this as being S, let's, some things just warrant a serious explanation, right? Now that we've got that figured out, well, let's find the longest carbon chain, which is these 4 carbons here. And again, it could be these 4 carbons. Either way, you're going to end up with the same thing. We're going to go 1, 2, 3, 4. Why do I number it this way? Because I have 2 substituents here, and I only have 1 here. So we have a 2-bromo, 2-iodo, 3-methyl butane, and it is S. So let's put that all together if I can remember. So it's S, 2-bromo, 2-iodo, 3-methyl butane. All right. This whole thing about the looking down the bond here, this is one of the limitations of teaching remotely, in my opinion, because it's a lot easier, to see where students are at when you're face-to-face in the classroom. All right, let's try the next one. We're coming off the heels of the stereochemistry chapter, so I'm sure you're all pretty quick at assigning stereochemical configurations. Remember, we want to find the longest carbon chain that has the most branching. It would be this one here. It wouldn't matter. I wanted to use a different color. 1, 2, 3, 4, 5, 6. Right, and you can see that you've got substituents here, 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 and here at 2, 3, 4, 5. If you had numbered the compound going this way, if you had gone 1, 2, 3, 4, 5, 6, you still would have had 2, 3, 4, 5. But you go with the red numbering because you have 2 chloro and 3 chloro, right? If you had 2 methyl, well, methyl comes after chloro because M comes after C in the alphabet. So the way that I have it numbered in red is correct. All right, let's figure out the stereochemical configuration at carbon 2. We go from group 1 to 2 to 3. That's clockwise, so it's 2R. Check out stereocenter number 3. This is number 1. This is number 2. This is number 3 over here. That's clockwise, so this is also R. So what do we have? We have 2R and 3R. I should write that down before I forget. So we have 2R, 3R, 2,3-dichloro, 2,3-dichloro, 4-isopropyl, 4-isopropyl, 5-methylhexane, 5-methylhexane. All right, here we go. A little bit of alkyl halide nomenclature on a Tuesday morning. Could anything be more exciting? Probably not. Probably not. All right, let's talk about the structure of an alkyl halide now, because that's going to be really important to us as we move forward in chapter 7. Greek letters are used all the time in organic chemistry. They're used in general chemistry too, aren't they? Greek letters are often used to label the carbons of the alkyl group attached to the halide. So whenever you have an alkyl halide, okay, the carbon that is attached directly to the halogen, that's called the alpha carbon. So this is an alpha carbon, right? If you look at all these things down here at the bottom, this is an alpha carbon, this is an alpha carbon, this is an alpha carbon. The carbon that is attached directly to the halogen is called alpha. Branching out from there, you go from alpha, beta, gamma, delta, right? Now, I think we're only really going to be concerned with alpha, beta, and gamma. I don't think we're ever going to talk about delta carbons a whole lot, even gamma carbons, really. But the amount of branching at that alpha carbon is what's going to affect the reaction mechanism. Okay, so you have to understand the branching to understand, is this going to be an elimination reaction? Is this going to be a substitution reaction? So you're going to see that we're going to analyze things in terms of the substitution at the alpha carbon all the time. There are 3 types of alkyl halides that you need to be familiar with. A primary alkyl halide, that's when you have 1 R group attached to the alpha carbon. A secondary, you guessed it, you got 2 R groups on the alpha carbon. And a tertiary, you know it before I did, right? There's 3 R groups on the alpha carbon. So again, alpha carbon directly attached. Beta carbons, if you have 1 beta, and that's what this is. This is the beta position. If you've got 1 beta substituent, it's primary. If you've got 2, it's secondary. And if you've got 3, there you go. It's tertiary, my friend. So primary, secondary, tertiary alkyl halides. If you've ever read, you know, maybe somebody here has read the book Silent Spring before, I don't know. Anyhow, alkyl halides were used as insecticides, still are. If you take a look at DDT and lindane, so DDT was used to, you know, combat malaria by killing mosquitoes. Anyhow, I think it, you know, was determined to be toxic to animals, so it was outlawed. And there's a whole interesting, you know, history behind DDT. So it's dichloro, diphenyl, trichloroethane. What about this chlorine that's circled here? I'll circle it in green. Would this be considered primary, secondary? This one is actually considered primary because it's only got one alkyl group. Exactly, Mackenzie, right? Because this is our alpha carbon here, and this is all the alkyl group here. So this is actually considered to be primary. If you look at lindane, I don't know if anybody here has ever had head lice before, but I wouldn't recommend it. But lindane is used in like head lice shampoos pretty often. Anyhow, here's our alpha carbon. Well, you have an R group here, and you have an R group here. So that means that this is secondary. Anyhow, some interesting chemistry behind both of these compounds, which we don't really have a lot of time to talk about. Let's see here. So we're going to talk about uses of organohalides in a second, but I want to give some practice to assigning a systematic name. So that's just not naming them as alkyl halides, but naming them as haloalkanes. So systematic means we're going to name it as a haloalkane. And again, you don't see anything here that you could really label or name as a alkyl halide. That would be way too complicated. Well, if we look at B, you can see the longest carbon chain has what? 1, 2, 3, 4, 5, 6 carbons. So this is some kind of cyclohexane. You can scribble that down. I like to write down all my thoughts here. Cyclohexane. And we've got a methyl group and a bromine, and they're both on the same carbon. Bromo is going to come before methyl, so it's a 1 bromo, 1 methyl cyclohexane. So we have 1 bromo, 1, sorry, you guys still see my screen? Yep. 1 bromo, 1 methyl cyclohexane. I'll have to bring that over here. There we go. 1 bromo, 1 methyl cyclohexane. What about the next one? Well, the first thing we got to do is address the stereochemistry. Again, I'm sure you guys are faster at it than I am by now. So this is going to be number 1. This would be number 2. This would be number 3. So we're going that direction. So it's R. Remember, we just go off the length of the alkyl group. Right? Chlorine is obviously number 1. Then you have a butyl group here. You have a propyl group here and an ethyl. Well, butyl and propyl are bigger than ethyl. So anyhow, it's R. And then we find the longest carbon chain, which goes like this: 1, 2, 3, 4, 5, 6, 7, 8. So it's some kind of octane. We've got an R. We've got a 4-chloro and a 4-ethyl. Chloro is going to come first because C comes before E in the alphabet. So we've got an R, 4-chloro, 4-ethyl, octane. That. And then the next one, let's see here. We've got the fluorine, which is going to be group number 1. This will be group number 2. This is group number 3. We go that direction. So this is also R. 10 out here. So this is some kind of R compound. The longest carbon chain has what? 1, 2, 3. No, that's not right. That's wrong. I have to number from over here. 1, 2, 3, 4, 5, 6. Right here you have a 2, 2. Here you have a 2, 2, 5. If I had gone in this direction, I'd have a 2, 5, 5. So 2, 2, 5 beats 2, 5, 5. So this is correct. So what do I got? I've got a 2, 2 dimethyl and a 5 fluoro. Well, F comes before M in the alphabet. So I have a R, my pen, 5 fluoro, 2, 2 dimethyl, 2, 2 dimethyl, And then my parent chain is a hexane. And there you have it, folks. And you can imagine that, of course, I'm going to ask you to assign a systematic name to a compound on quiz 7 for sure. I mean, it's a big chunk of this section, so you need to know how to do that. Give me a thumbs up if you're feeling good about alkyl halide nomenclature. You're like, yeah, I just need to practice it a little bit. But again, you know what's one of the most beautiful things about nomenclature is, just like I promised you, and I told you, I remember saying this in chapter 4, that I don't like to promise things to people, but if you understood alkane nomenclature, all those rules that you learned, they weren't just a one chapter thing, were they? I know that it took all of you time and that you worked on memorizing terbutyl, isobutyl, you know, all that stuff, but it can all be used in this chapter. It can be used in the chapter after. It can be used till the end of your time studying organic chemistry. You're like, end of my time studying organic chemistry. I plan on studying this for the rest of my life. I love it so much. Well, uses of organohalides. Organohalides show up all over the place, you know, even in dry cleaning. So the solvents that are used in dry cleaning are usually halogenated solvents. The structure of the molecule determines its function. Um, and functions of organohalides include things like DDT, which I had the structure, where was it? Right here. So this is, again, DDT. It's kind of a cool compound, interesting looking compound. Dyes, you know, drugs. There's all kinds of antidepressants. An example of that would be something like Prozac. The Prozac has fluorine in it. Splenda. So Splenda has chlorine in it. It's called sucralose. So sucralose. And there's some interesting reading in the chapter about that. What else? Many more. I want to see, did I put anything else? You know, a funny thing that I got asked a number of years ago, I don't remember when it was, but was about PCBs, right? There's PCBs and they're mentioned in our textbook. A PCB, so PCB is a polychlorinated biphenyl, so polychlorinated biphenyl. And a polychlorinated biphenyl, those are used as coolants and insulators, but they're determined to be really bad for the environment. My father told me a crazy story about PCBs one time, that my grandfather, his father, was a contractor, and they were pouring foundations when my dad was a teenager. And my dad's in his 70s now, but he said they were pouring foundations, and they would have to lubricate the sides of the foundations before they poured the cement into it. And he told me that one day his dad showed up, my grandfather showed up with all this oil that he had gotten for really cheap. You know, that he got it for basically nothing, and he was going to use it to lubricate all these forms. And anyhow, it came out of a transformer, right? You know, from a, you know, on a telephone pole. And so it was the oil that came out of that. So it was just loaded with PCBs. And my dad said that they were out there in the hot sun with their shirts off and rollers and brushes, just brushing this stuff on. He said, well, I never haven't gotten cancer yet. So, but anyhow, it's really dangerous. But the funny thing is that, and I guess this is going to end up on YouTube, but whatever. A student asked me, that he's like, are you talking about PCP? PCP, is that what you mean? Like PCP, that's phenylcyclidine, which is angel dust, which is something completely different. Okay, so PCP, that's used for its mind-altering effects. It's got nothing to do with PCB. So PCB and PCP, two very different things. Anyhow, I never forgot that question. I thought it was really funny and a perfectly honest mistake. You know, PCB and PCP, they sound alike. All right. Anyhow, let's move on from there. So that's the end of section 7.2. Let's get into the heavy stuff here and talk about the SN2 reaction. You remember at the very beginning of today's lecture when I mentioned substitution and elimination, I said that first we would look at an SN2, and then we're going to look at what's called an E2 reaction, and then we're going to look at an SN1 reaction and an E1 reaction. But I think that the focus of our time today is going to be spent talking about SN2 and E2 reactions. Okay, we're not going to look at SN1 and E1 until quite a bit later. So the substitution reaction, right? We talked about substitution reactions already. I even drew you the mechanism that's shown here on this slide. It involves a loss of a leaving group and a nucleophilic attack. Now, there's two possible ways that you could have a substitution reaction occurring. You could have a concerted mechanism. What does concerted mean? A concerted reaction, or a concerted mechanism rather, means that the bond breaking for the loss of the leaving group and the bond formation during the nucleophilic attack are occurring at the same time. So, you know, scientists have to have a fancy word for everything, right? Concerted means nothing more than at the same time. So you see that the nucleophile is attacking the electrophilic carbon, this one here, and you're losing your leaving group, and they drew 1, 2 arrows, right? The nucleophilic attack and the loss of the leaving group occurring simultaneously, and that is a concerted mechanism. The other possibility is to have a stepwise mechanism. Well, how does that happen? First, the leaving group is going to leave, so it just goes away. All right. You make a carbocation, and then the nucleophile can come in and attack. Now that's 2 individual steps. First, the loss of leaving group, and then the nucleophilic attack. This isn't covered until section 1 or 7.10, the 2-step process. So the SN2 reaction is the concerted reaction. Okay. One of my friends told me this in my undergraduate days. He said it's SN together, right? Both steps are happening together at the same time. SN together. Everything's happening at the same time. The nucleophilic attack and the loss of leaving group, right? The concerted fashion. Now, in terms of reaction rate, so this is kind of going back to Gen Chem 2 and going back to our classes chapter 6, the rate of reaction is going to depend on both the concentration of the substrate, right, your alkyl halide, and the nucleophile. How would I write out the rate expression for that, the rate law? I'd say that the rate is equal to the rate constant multiplied by both the concentration of the substrate and the concentration of the nucleophile. So the rate law is where we get the name SN2. The S stands for substitution, the N stands for nucleophilic, and the 2, again, that's the part that comes from the rate law, it stands for bimolecular. Okay, I'm not going to ask you about the units of K here. So if you have rate, which is moles per, or reciprocal molar times reciprocal seconds, moles per liter per second, it's equal to, you know, reciprocal moles times reciprocal seconds. Anyhow, I'm not going to ask you about that. So that's a Gen Chem 2 thing, but I'm not going to get into the units of it or anything. But what I do want you to be able to do is answer a question like this, okay? And this is a real classic question that shows up on almost every final exam in every state, in every country, in every province in the world where people are studying organic chemistry. So follow along with me. It says, this reaction, this one right here, is a substitution reaction, and it exhibits second-order kinetics and is therefore presumed to occur via an SN2 process. So how would I write out the rate law? I'd say rate is equal to K, the rate constant, multiplied by the concentration of the alkyl halide, right, the substrate, and multiplied by the concentration of my nucleophile, right? I leave the sodium out, it's a spectator ion. So there's my rate law for this reaction. Okay, question A asks us, what happens to the rate if the concentration of 1 iodopropane, which is this molecule, is tripled and the concentration of sodium hydroxide remains the same? Could anybody tell me what would happen to the reaction rate if I was to triple the concentration of 1 iodopropane? And it's not a trick. It's just the most basic possible answer you could have. What if we assumed that our rate constant was 1, the concentration of our iodopropane is 1 molar, and the concentration of our hydroxide is 1? Then we'd get a rate of 1. So if we were to take rate and we were to say it's equal to 1, our rate constant, multiplied by 3, because we've tripled the concentration of the iodopropane, and then 1 because we haven't changed the concentration of the hydroxide, what happens? It's going to go up by 3 times. So the rate is tripled. Tripled. Okay, using the same rationale, then how would we answer B? If the concentration of 1 iodopropane is the same, and we double the concentration of NaOH, what would happen then? Who could tell me? It's going to go up twice as much, right? The rate is doubled. Okay, and then finally, what would happen if we doubled the concentration of iodopropane and we triple the concentration of sodium hydroxide. Well, then we'd have the rate is equal to the rate constant multiplied by 2 times 3. What's 2 times 3? It's 6. So the rate increases, we'll say sixfold, or 6 times as much. Anyhow, 6 times faster. All right, so you can see it's not a complicated question. Everybody can multiply by, 1 by 2 and 1 by 3 and 2 by 3. It's just a matter of interpreting the rate law. So you need to know that since it's an SN2 reaction, the rate depends on both the concentration of the substrate and the concentration of the nucleophile. If you really want me to get ahead, which I'm sure you don't, but if if you want to know where we're going with this at the end of chapter 7, what you're going to see is we're going to see reactions where the rate, and we're not covering this yet, it'll be later, but we're going to see reactions where the rate is going to be equal to the rate constant multiplied by the concentration of the substrate only. It's a first order reaction, and that's what an SN1 reaction is. But that's for later, okay? We'll put here later, okay? Because we've got a lot to talk about SN2 reactions first. But so far, we've talked about the effect of the concentration of the substrate and the nucleophile. Because it's a second order reaction, the reaction rate depends on both concentrations. Well, what about the stereochemistry of this SN2 reaction, this substitution nucleophilic bimolecular reaction? When the alpha position is a chirality center, a chiral center, a stereogenic center, whatever you want to call it, what you see is that a change in configuration occurs. Okay, so we have this molecule over here. You can see the stereochemical configuration is S. You can practice all the time. You have 1 to 2 to 3. No, that's a 3. So we go like this, but the hydrogen's coming out in front, so it's S. Good. So they did it correctly. Anyhow, but what happens is if you were to do the SN2 reaction with this hydrosulfide, so this is hydrosulfide ion, what you see is you get an inversion of the configuration. It goes from S to R. If you started with R, you'd end up with S. Okay, we say that this is stereospecific. Stereospecific means the configuration of the product is dependent on the configuration of the substrate. Right? Again, if you start with S, you get R. If you start with R, you get S. So this depends on this. Right? That's the whole point behind something being stereospecific. Well, what the heck is actually happening here? Okay, what's actually happening here? What is happening is a process that's called backside attack. Now, you can probably guess what that means. It's attacking from the back of the molecule. What's the front and the back of the molecule? Well, we're going to talk about that in a second. But it says here that electron density repels the attacking nucleophile from the front side. So what that means is the nucleophile, the hydrosulfide, is actually attacking from over here. Now, why is that? The first point said electron density is going to repel the attacking nucleophile. So all the lone pairs over here, right, this is delta minus, and it's going to repel the negative charge here. So that means this is why the nucleophile is not going to attack over here. It doesn't happen. Okay, that's why it's going to try to attack from the back. That's why it doesn't try to attack like this. It's coming too close to this negative charge, and it tries to avoid that. Okay, so that's point number 1. The next point is it says the nucleophile must approach the backside attack to allow electrons to flow from the HOMO of the nucleophile to the LUMO of the electrophile. I am not going to ask you about HOMO and LUMO. Okay, I'm not going to ask you about that at all. And the whole point of proper orbital overlap. Okay. I'm not going to ask you about that. I'll get you to read it. It doesn't take you very long to cover that section. But the whole idea is nothing more than it wants to avoid this partial negative charge on that bromide, right? Like charges repel one another. And so that's why the hydrosulfide is going to attack from the back face of the molecule. And that's what we call backside attack. Okay? So it says here to draw the transition state for this reaction. What's the transition state going to look like? I'm not going to ask you to draw a whole heck of a lot of transition states in Organic Chemistry 1, but what I want you to understand is that during the transition state, remember those when we looked at the reaction coordinate diagrams in chapter 6, we said the transition state was the energy maximum, right? If we had something that looked like this, okay? We said that these parts here, those were transition states. Okay. Well, a transition state is where what? A bond is partially broken and another bond is partially formed. We use the double dagger symbol to represent that we're drawing a transition state. So what's the transition state going to look like here? Let me show you what it's going to look like. We have the carbon where the nucleophilic attack is going to occur. I'm going to draw it in blue. Then we would have our methyl group like this. We have our hydrogen in the back like this. We have our ethyl group coming down. But then instead of drawing bonds to the sulfur in a bond to the bromine like that, well, that's not accurate because then I've exceeded the octet rule of my carbon. So what we draw is a dashed line like this to the sulfur. We draw a dashed line to the bromine like that. What does that tell us? It tells us that these are not bonds, right? This is an intermediate where the bond, this bond is being broken and this bond is being formed, right? That's what's happening. So to represent it more accurately, we put a delta minus over here and a delta minus over here to say, well, this is partially negative because it's the nucleophile coming in, and this is partially negative because it's taking the electrons from this bond to become the bromide ion, which is kind of lost over here. So that's what a transition state looks like. Now, it says here to practice drawing the transition states with this skill builder. I recommend that you practice drawing maybe 1 or 2 transition states just so you have it in your brain, okay? Just so you know what a transition state is. There's a bond being broken, there's a bond being formed. It's highly unstable. You can't isolate it. It's just a state that the molecule passes through as one bond is broken and the other bond is formed. Now, what I think is even, or what is much more important, would be to draw or to do a question like this, where it says draw the product for the following SN2 reaction. So we're going to draw the product that's formed when we react S2-chloropentane with sodium hydrosulfide. Well, let's see here. So again, this is called sodium hydrosulfide. Okay, well, how do we draw S2-chloropentane? My strategy is to do this. I'll start by drawing 5 carbons, 1, 2, 3, 4, 5, like that. If I number them 1, 2, 3, 4, 5, right? That's all good. So I'll put the 2-chloro here, and will I draw it with a dash or a wedge? I always start with a dash, check it, and if it's wrong, then I just fill it in, okay? So that's kind of my strategy for doing it. So we'll draw a dash like this to our chlorine. That means the hydrogen is coming out in front, right? So we have number 1, number 2, number 3. This is going R, so that means it's S, so it's good. So this is S2-chloropentane. And then we're going to draw what happens when we react this with sodium hydrosulfide. So here's my hydrosulfide ion. This is my nucleophile, right? This is my electrophilic carbon. So this is my electrophile or my electrophilic center. This is my nucleophile. This is going to be a nucleophilic attack followed by a loss of leaving group because these 2 steps occur simultaneously in an SN2 together reaction. But when we draw our curved arrows, so we draw the nucleophilic attack and the loss of the leaving group like that. When we draw our final product, though, 1, 2, 3, 4, 5, what do we have to do to our bond to the SH? Should this bond be a dash or a wedge? And it's not a trick. Would it be a little dashed bond or would it be the shaded in bond, the wedge bond? If we go back in our notes, okay, we see that an SN2 reaction is going to proceed with inversion of configuration. So whatever was a dash would become a wedge, and whatever was a wedge becomes a dash, right? That's the whole idea behind inversion, right? We have inversion of configuration. So let me go over it with you again. So if this is S, right, this is an S stereocenter over here, or maybe I could write it below like this. So this is S over here. So that means I'm going to draw this with a wedge. Right? That's the whole idea behind inversion of configuration. Now I go from 1 to 2 to 3 like this, and this is R. So I go from S. Come on. What's going on here? From S to R, like that. Does that help? So remember, the SN2 occurs with inversion of configuration. So that means if you have a wedge, okay, it becomes a dash. And if you had a dash, it would become a wedge. Okay, that's the whole idea behind inversion of configuration. It's like an umbrella flipping in the wind is how we can describe it. The SN2 reaction. There you go. So now you've drawn the mechanism for your first SN2 reaction. Well, what about the rate of reaction for an SN2? How does the substrate affect the rate of reaction? How does it affect the kinetics? Since the reaction occurs by a backside attack, and it's two steps at the same time, the nucleophilic attack and the loss of the leaving group occur simultaneously, the less sterically hindered your electrophile is, the more reactive it will be. Take a look at the comparison here. We're going from a methyl halide to a primary, to a secondary, to a tertiary. And you can see that the methyl is the most reactive and the tertiary is unreactive, completely unreactive. It says that to rationalize this, look at the reaction coordinate. But we don't even have to do that, really. If you just think about the steric hindrance, right? If your nucleophile has to do a nucleophilic attack, right? This carbon only has 3 hydrogens attached to it. That's not very sterically hindered, my friend. If the nucleophile has to attack over here, well, then there's only 1 substituent here. So that's not too bad. If it has to attack the secondary, now you got 2 big old bulky groups in the way. It gets a lot more difficult. And the reason why the nucleophile can't even attack here, can't squeeze in, is because you got so many substituents in the way, right? You got too many substituents in the beta position. All right, so that's why a methyl halide is going to be most reactive, followed by a primary, followed by a secondary, followed by a tertiary. Here's a table that summarizes what I was just telling you, okay? This is what we just looked at. What's on the left side of this table here? What's going on in this table is it's showing the effect of alpha and beta substitution on carbons and how it affects the rate of an SN2 reaction. Let's take a look at the left-hand side of the table first. So we have an alkyl bromide. We're treating it with iodide, and we're making an alkyl iodide. Okay, so this is an SN2 reaction, right? Your iodide is coming in here. SN2, bada boom, bada bing. Okay. Well, like we just said, as you go from a methyl to a primary, to a secondary, to a tertiary alkyl halide, right? This is primary, this is secondary, this is tertiary. You can see that the rate decreases dramatically. And then once you get to a tertiary, it doesn't even work. Okay, it doesn't work at all. Now, based off of this information, it might be a knee-jerk reaction to say, okay, well, if I have a primary substituted alkyl halide, it's just going to go like stink. No matter what, the relative rate is always going to be, I'm going to get a good reaction. Well, hold on. Check this out. Look what happens. Again, we're starting with this molecule here. It has a relative rate of 1. What happens if you put a substituent on the beta position? Right, so if you have, this is your beta position, right here, there's nothing on it. There's just 3 hydrogens. Now, if you add a methyl group, you can see that it changes the rate a little bit. If you add 2 beta groups, it changes it, significantly. And then if you have 3 beta groups, this is still a primary alkyl halide, but it's practically unreactive. Junk. It's not going to work at all in an SN2 reaction. So this is, the book alludes to this, and what he says is really great. In our textbook, I don't know exactly which, I know it's in this section, but I don't remember the paragraph. But he says something to the effect of, this is why it's so great to understand what's going on in organic chemistry rather than to just memorize it. Okay. If you understand what's going on, it makes, a lot of sense. If we do take a look at the reaction coordinate diagram, and this is an example that comes straight out of our textbook, right? We have our substrate, we have our nucleophile. Here they're showing a reaction between methyl bromide and a cyanide ion. So the cyanide is going to do the backside attack, right? You lose your leaving group. This is what your transition state looks like. Okay. Well, here I've only got 1, 2, 3 protons. So this is going to be highly reactive. And remember, the rate of reaction is related to what? The activation energy. So the activation energy here is going to be relatively low compared to something like a secondary or tertiary substituted alkyl halide. If we compare the relative activation energies here, as we go from a methyl to a primary to a secondary, you can see, again, what is the reaction rate related to? It's related to the activation energy, and we saw this in the Arrhenius equation in chapter 6, right? Little k is equal to A times e to the power of negative EA divided by RT. Anyhow, that's neither here nor there right at the moment, but the idea is that the reaction rate depends on the activation energy, and the more substituents you have, the higher that activation energy gets. Notice that they don't even have a reaction coordinate diagram for a tertiary substrate because it's too slow to measure. It's too useless, okay? There's all kinds of reactions in organic chemistry that might seem nice on paper, but when you go to try them, the reality is they just don't work, okay? So here's that point that I was talking about earlier on. If you look at this molecule, this is called neopentyl bromide. That's the common name. Anyhow, if you look at neopentyl bromide, it's a primary alkyl halide. Look, your alpha only has one thing attached to it, right? The other two things are hydrogen. So it is a primary alkyl halide. But look at it. Its SN2 reaction is completely useless. It doesn't react in an SN2. Why? Because you have so much branching on the beta carbon that it just makes it too sterically hindered for an SN2 reaction to occur, right? You see, you get this big old tert-butyl group here. It's just too in the way for an SN2 reaction to occur. And this is the whole point, again, and I'm repeating myself, where he says, this is why you need to comprehend what's going on in organic chemistry rather than simply memorize it. Are there things in organic chemistry that you have to memorize? Absolutely. Okay, I would be a liar to say that that's not true. Okay, but the best way to do anything in organic chemistry is to have an understanding of what's going on. I know it's getting a little late here and I'm thinking about taking a break, but I want to share a couple more thoughts with you. Section 7.4 isn't a long section, but it's an important section. And there's a couple of tables I just want to show you and make some recommendations here. So in terms of a nucleophile, right? Everybody who's hearing the sound of my voice by now, you all know what an electrophile is. We talked about that in chapter 6. You all know what a nucleophile is. We talked about that in chapter 6. And now we've taken those concepts into chapter 7. We're looking at reaction rates. And now we're going to talk about, what makes a good nucleophile? What makes a good nucleophile? When can I look at something and say, hey, that's going to be a nucleophile, right? Because it's going to depend on the situation. Well, there's some factors that we have to take into account, right? Charge and polarizability. We looked at these in section 6.7. Charge is pretty obvious. Charge is, if you have a negative charge, you're going to have a better nucleophile. If you take a look at hydroxide and water and compare the two, well, hydroxide is going to react faster with iodomethane. Why? Because it's got a negative charge. Of course, it's going to react faster with this partially positive carbon with the electrophilic center. So if you have, again, a negative charge, you're going to have a better nucleophile. Now, polarizability, I covered that a little bit in the last chapter. Polarizability, again, refers to the ability of a nucleophile to distort its electron cloud. Okay, so basically the whole point of polarizability is that the bigger the atom is, the better nucleophile it'll be. And that's why when we compared, for example, what did we talk about? I think we talked about hydroxide versus hydrosulfide. Hydrosulfide is a more powerful nucleophile. Even though sulfur isn't as electronegative, it's a bigger atom, so it's able to distort its electron cloud and be a better nucleophile. Well, commonly used nucleophiles that you're going to see come up all the time in this class, okay? I would suggest memorizing this. And when I say suggest, I'm kind of suggesting like my dad would suggest something, which is all he means is that you got to know, or that or that he wants you to do. I suggest that you do this, meaning you must do this, right? Anyhow, so strong nucleophiles. Now, if you're like, I hate memorizing stuff, well, you probably notice right away that everything that's a strong nucleophile is get a negative charge on it. So that's kind of helpful, right? Everything that's a strong nucleophile has got a negative charge, whether it's iodide, bromide, chloride, hydrosulfide, a thiolate. So this is called a thiolate. Maybe I could scribble that in there for you. A thiolate, okay? A hydroxide, an alkoxide, a cyanide, right? These are all good, strong nucleophiles. Weak nucleophiles are going to be things like water or an alcohol, okay? There we go. So again, you should be able to determine if a nucleophile is strong or weak. Anions are going to be strong nucleophiles. Polarizable atoms. So a polarizable atom, again, would be comparing, say, sulfur to oxygen. Sulfur is more polarizable. But hold the phone, okay? This is where organic chemistry really gets, a little juicier, so to speak, is that not only do we have to consider our reagent, our substrate, and our nucleophile in an SN2, but we've also got to consider solvent. If you think about everything that you've done in chemistry up to this point, I know that you've looked at solvents in chemistry. Okay, you've all passed Gen Chem 1, Gen Chem 2. But if you think about, you don't talk about solvents a ton in chemistry class. Okay, really until you get to this section. So now we know that an SN2 reaction is this. We know it's the rate of reaction is equal to the rate constant multiplied by the concentration of my substrate, which is your alkyl halide, multiplied by the concentration of your nucleophile. It's a second order reaction. I mean, that's a lot to think about. But now you've even got to think about, well, what am I dissolving everything in? What's my solvent going to be? But look, I'm going to explain it to you as simply as I possibly can. Okay, it says here that you need what's called a polar aprotic solvent for an SN2 reaction. Okay, now if you're like, what the heck is a polar aprotic solvent? Let me show you. All of the solvents in here, and there's a whole hell of a lot of them, right? They're all polar. Notice it says protic over here, and then it says polar aprotic over here. Well, I'm here to tell you that everything over here is polar too, right? Water is polar, alcohols are polar, ammonia is polar, and so is acetic acid. So everything in this table, everything is polar. So what's the difference between protic and aprotic? You can probably guess, right? Notice that the protic solvents, they all have a hydrogen, which is a proton, highlighted in red. Well, what's so special about all these damn protons? Pardon my language. You notice that all of them are either attached to an oxygen or a nitrogen. So all of the protons that are highlighted in red, they're all capable of what? Hydrogen bonding. Okay? So the difference is that a polar protic solvent is one that can participate in hydrogen bonding. And again, all of these can. So water, well, of course, water can hydrogen bond. An alcohol can, right? Ammonia can hydrogen bond, okay? And so can a carboxylic acid, like acetic acid. Now, polar aprotic solvents, these are solvents that you haven't probably even seen all that much. I know you've seen acetone a bunch of times. Some of you probably even own acetone, right? You're like, well, I use nail polish remover, every week or something. Well, that's what, nail polish remover is. Notice that there's a dipole in acetone, right? There's a dipole right here. It's a polar molecule, but it's not protic. There's no hydrogen directly bound to the oxygen. So it's polar, but it's aprotic. The next one is DMF. First post I ever made on Twitter was about a book called DMF. It's an actual book written about one solvent. I saw it in a friend's office one time. I was like, I got to read this book. Anyhow, so DMF is a solvent that is widely used in organic chemistry. It's water soluble, which is kind of cool. But you can see there's a strong dipole in DMF. There's an oxygen and a nitrogen in it, but there's no bond between those atoms and a hydrogen. The next one is HMPA. If you want to have a bad day, if you're having a good day and then you want to ruin it, just get HMPA involved in your life, because hexamethylphosphoramide is not only highly toxic, but it has to be distilled every time you use it. You got to set up a distillation, and you're thinking, how hard can it be? It is very complicated to distill. I had a friend who was You know, a guy I considered a borderline genius. And I remember him telling me, he's like, it took me all day just to distill some HMPA. So, you know, I try to avoid using HMPA when I can. Again, it's highly toxic, but you can see that it's got a dipole in it. And what's great about Chemistry 3101 is that you actually don't have to use HMPA. You don't have to actually touch it. You just have to write HMPA, right? And that's done, right? That's the great thing about organic chemistry on paper. Next, we have dimethyl sulfoxide, DMSO, which has a beautiful dipole in it. But again, there's no bond between the oxygen and a hydrogen. Dimethyl sulfoxide is, again, a widely used solvent. I've used it millions of times in my life. It gets absorbed through your skin instantly. So if you're not wearing gloves, and I didn't wear gloves for years, if you see my hands, you'll realize that I didn't wear gloves for years. It gets absorbed through your skin really quickly, and this is going to sound funny to you probably, but when it goes through your skin, I don't know if anybody has ever tasted canned corn before, and I'm not kidding, canned corn that's not heated up, which I wouldn't recommend eating, but if you ever have, you have that taste in your mouth in seconds when you spill DMSO on your skin, so it's not fun. The next one is acetonitrile. The worst accident I've ever seen in a chemistry lab involved a reaction between a reagent called lithium aluminum hydride, which we'll learn about later, and acetonitrile. It caused a mega fire and explosion, which was just really scary, and a guy got hurt really, really bad. Anyhow, I'll tell you about that another day. But it's got a dipole going this way, and there's also a dipole going this way because an sp hybridized carbon is more electronegative than an sp3. I know it's not covered in our textbook, but it's true. So it's highly polar, but it's not protic. So those are all those solvents. And the reason I kind of walk you through all of them is because I don't want to just throw them up on a table and be like, know this. You know, I like to talk about things with my students and try to, you know, show you what these are, when they're used and stuff. So when we're doing our SN2 reaction, when you're doing an SN2 reaction, you want to use one of these solvents in here, either acetone, DMF, DMSO, acetonitrile, or HMPA. Why? Why do you want to use that, and why do you not want to use one of these? Why do you avoid water for an SN2? Well, the reason has to do with what a protic solvent can do. A protic solvent has the ability to stabilize both a cation and an anion. And if you think about what that's saying, is if the solvent can stabilize an anion is the nucleophile, right? If the nucleophile is stabilized, that means it's not going to be reactive. And that is why protic solvents are no good for SN2 reactions. Let's take a look over here. So if you have a nucleophile and it's in a polar aprotic solvent, it's going to have a higher potential energy. That means it's going to be ready to react. Wants to react, right? But if you have it in a protic solvent, it's stabilized, therefore it's going to be unreactive, right? It's too low in terms of its potential energy. If you want to talk about it in terms of, you know, how does it stabilize it? How does the polar protic solvent stabilize a nucleophile? Let me show you. Here's the problem with a polar protic solvent, like water, for example. Let's say you have NaCl, right? It consists of a sodium cation and a chloride anion. Well, if you go back in this table, way back here, we saw that a chloride is a dandy nucleophile. Okay? Chloride makes a great nucleophile. So what's the problem then? The problem is that if you put sodium chloride in water, the chloride is rendered unreactive. Why? Because not only can the oxygen of water stabilize the positive charge of the cation, right? Because remember, water is a polar molecule. It's got a nice tasty dipole where you have a delta negative here, delta plus here. Well, the delta negatives on the oxygen can stabilize the cation. Okay, well, whatever. But hold on. The delta pluses on the hydrogens can stabilize the anion. That's not good. If the anion is stabilized, it's going to be unreactive. So you can say here, it's rendered unreactive. That's not useful. We need it to be reactive. We need it to react. So why does it react in a polar aprotic solvent? Well, they show you here with DMSO. Okay, so DMSO is a polar aprotic solvent, And you can see that there is a dipole in the molecule. However, the delta plus, it's too sterically hindered to stabilize the chloride. It just won't do it. Now, the DMSO molecule can stabilize the cation, right? So, I mean, I didn't plan on doing this, but if you were to draw the DMSO molecule, let's say, like this, okay, right? You have the delta minus up here. Well, that can stabilize the positive charge on the sodium. Anyhow, so the DMSO can stabilize the cation, but it can't stabilize the anion, and boom, it's going to be super reactive. You know, after all that spinach that I've been talking about for the past 10 to 15 minutes, the summary is this. Aprotic solvents are best for SN2 reactions. Okay, that's it, man. That's it. And you have to just be aware of that. It's going to come up all the time when we talk about SN2 reactions. If you're interested, if any of you are interested in writing, let's say, an MCAT exam, and I'm sure there's at least somebody in the class that's interested, or maybe a PCAT, or maybe, you know, a DAT exam, right? I can promise you, and I don't like to promise things to people, the SN2 is definitely going to come up in any one of those exams or any other standardized exam that involves organic chemistry. All right, so SN2, very important. Well, the next section deals with biological alkylation and SAM, which is an acronym that I'll let you read about. This is something that you will talk about in your biochemistry class, and I know that several of you have enrolled in biochemistry or thinking about taking biochemistry. So we skip it in Organic Chemistry 1, but if you want to take the time to read that, go ahead and do that. I highly recommend it.